So this is something that we wondered about. So we were wondering that, okay, you are testing some software and you collect the test coverage, and as the coverage goes higher, you find defects and remove them. So obviously, for higher coverage, you should get higher reliability. And then I found that nobody has made a direct connection between test coverage and reliability, or test coverage and number of defects found. So we thought that we will do a study, and so we looked at test coverage. But before we go forward, let me mention about the test coverage measures. Now, there are software test coverage tools available, and these tools measure coverage of different things. So, for example, tools will cover. Sometimes they will count the statement coverage. Or sometimes they will count block coverage, which is sort of similar. So what fraction of the statements have been covered, or what fraction of the blocks have been covered? Basically, by block we mean a block of statements within which there is no branching. And then there is branch or decision coverage. So what fraction of branches have been covered? And then you have other coverage measures. Now these are structural coverage measures, and there are some coverage measures that include involve data defining and use. So there are other measures, but I guess you can look them up in the literature. And people have shown that there is a subsumption hierarchy. And let me give you that hierarchy. So you have here, so they have something called statement coverage. And branch coverage. There is something called P-use coverage, and then some others. So these are the stricter measures. So if you get 100% P-use coverage, then you will definitely get 100% of this. And if you get 100% branch coverage, it's guaranteed that you will have 100% statement coverage. People have mathematically proven that coverage. And so this is called the subsumption relationship.
There is like an addition to this subsumption relationship that was added like a year and a half ago, I guess, by Chief Offit. And he suggested a new measure that criteria, the coverage criteria that he calls prime paths. And he proves, like in his book, that it actually subsumes all these other ones.
Oh,
so
I see.
it's
Okay.
like at the top of the.
Yeah. So there's actually a set of relations people have investigated. So this is just a part of what people have proposed.
Yeah.
So if you can find some measures, there was a famous paper by Eileen Wyuker, and then some people have extended so the work that you have seen. So these are some of the things that we have used. Typically, for all practical programs, people are happy if you get 80–90% branch coverage, and you almost never get 100% PU's coverage. So this is what we thought about. So we noticed that if you would, let us say that you are testing some software, and here is time. And you find, now here is your mu t. And as you will remember, mu t is the total number of defects found. So here is your mu t. So would go like this. And let us assume that you switch to your testing strategy at this time. Then what will happen? That your defect finding rate would go up if you will switch your testing strategy. Now here, now what if you would, instead of total number of defects, if you will plot coverage, let us say C is coverage, then you will notice that the coverage will go up like this, and when you switch testing strategy, your coverage will start going up like this. In other words, with a new strategy, you will get some more efficiency in terms of covering software more. But what will happen, we ask this question, if you will plot coverage with the number of defects found. And of course, you know, coverage goes between 0 to 1 or 0 to 100%, right? And we did some analysis, and according to our analysis, you will get a plot like this. And this part of the plot is linear. And here it bends, and we call this part of the plot a knee. And let me give you the mathematics we did. And here is the mathematics. So we assumed that so here are the assumptions we made. So this is, of course, the model, which is by, I guess you could say, it goes by my name, my student, Denton, and other people who worked on this idea. So one of the assumptions was that this plot is governed by the logarithmic model. And as I have mentioned, logarithmic model actually fits quite well most types of data. And here we assumed that coverage in terms of time follows a logarithmic model. And of course, we assume that mu t is given by the logarithmic model, which happens to be okay, don't worry too much about the parameters. We are going to skip the derivation. So basically, this is a logarithmic model, and this one, let's assume, follows a similar logarithmic model. So notice that this here is a function of t, this here is a function of t, and what you could do is you could eliminate t by using the two expressions. So you could see a coverage, you could say, is a some function, and okay, don't worry too much about what these mean, but if you are interested, you can look it up in our paper. You might think that this looks like a complex expression, but we found that with typical values, okay, I seem to have a parenthesis missing, right? Okay. And of course it is true only, so this is the defect coverage. This is the defect coverage, and here is some test coverage measure. So your C sub I could be branch coverage, it could be statement coverage, it could be whatever kind of coverage measure. So basically I means I could be anything, and this is your defect coverage. And for it can be shown for large, now this looks complex, but for large value of C sub I, you can see that this expression becomes a linear expression. And this is for C sub I greater than C sub I ni. So this is your C sub I, and this here is the ni. And now notice that now this is defect coverage, and mu is the number of faults, and coverage of course is a normalized number which is between 0 and 1. So here this could be mu, or this could be in C sub 0, which is defect coverage. Or you could, if you prefer, you could keep it in terms of mu. So we have shown that after a need, this indeed is linear. And now we always get into arguments. Well, we have plotted some data, and we got some data, and the data, we actually, when we originally formulated this using, we had just a little bit of data. So we did algebraic analysis, and it fitted that little bit of data. And later on we found some better data, and the better data, it fitted our model quite well.
So how do we interpret this diagram in terms of testing? Like before the knee and after the knee, does that depend on what kind of faults we're revealing? Is it like the easy or the hardest? Or?
Yeah, basically notice that here, as you go to higher coverage, it becomes harder and harder to get extra coverage. So here, so as your testing progresses, your progress here would be fairly fast. But when you're here, your progress will be very, very slow. So you will, as you approach here, you will find it's harder and harder to approach 1. So notice that this x-axis is not time, it's coverage. Because we have removed the time. So typically what you will see is that in most cases, you're doing branch coverage, people would sort of stop here. They will say, okay, this is about as much as we can get, and we are not, we stop testing here. So then, now if we assume that this linear trend holds, Then you can extend this linear trend, and you can see